Okay, IED. Today we're going to start talking about how to create holes in computer-aided drafting software. And in order to first start that, we kind of need to know how to find and identify what a hole would actually look like. It sounds really simple in concept, but as it turns out, it's not nearly as straightforward as you would think, because whenever you see a hole, you're like, oh, it's just a hole. But there is a lot of detail on how holes are used. It's a very important concept in engineering. So here's what we're going to do. Our goals for today is we're going to learn how to read and interpret a hole note to identify the size and type of hole specified. And we're going to create and constrain a 3D model to represent the physical characteristics of a physical object. And we're going to have some on-shape goals as well too. We're going to be like creating sketches, we're going to be extruding features, and hopefully we're going to make some complex hole features. This will probably take a couple of days. I don't expect all of this to be done all in one day. And we'll kind of see where we go with it. The stuff that we're going to need is the Trammel Toy 3D printed parts, or the ones that we're going to develop in Onshape, especially for my digital students. We'll actually develop these digitally, and I'll provide them to you guys. Dial calipers, instead of using dial calipers, if you're digital, you're going to end up using the Onshape measuring tool in order to be able to find out the lengths and the radiuses or diameters that we need. So really what this is going down to is everything that you make, every part that gets made, the sizes and the dimensions of the object, including the holes, has to be documented. If you don't document the sizes or the dimensions of things, then people aren't going to know how to create it or reproduce it. So the CAD modeling will allow you to have scaled uh, versions of your objects without having to worry about it. Okay, so I'm going to go ahead and let's see here. Engineers in a variety of disciplines experience a need to record the details of how existing things are constructed and assembled. Often it is convenient to create a sketch either by hand or using sketching software on a mobile device to document information gathered when away from an office or a computer. Engineers can later create a CAD model using the information they gathered. So what we're going to be doing is we're basically going to be doing that as well too. We're going to have a physical object and we're going to be recording the dimensions of it before we can actually get it like straight into the CAD software. So today we're going to specifically focus on holes themselves. So, holes are basically whenever you have a circular, round um, cut that goes through an object. And there are two different types of holes on the face value of them. There's a through hole, and then there's a blind hole. And if you look at the examples that I have down here, a through hole is whenever you take like a drill and you just like pass it straight through completely into like a piece of plywood or MDF or something like that, and you drill through it, you can see the other side. If you can see through the material, then it is a through hole. If you cannot see through it, so like if you drill down, but you're only drilling so far, if you cannot see all the way through the material, then it is not a through hole, it is a blind hole. So we have a through hole and we have a blind hole. And the tops make a difference on what the features are. So if it is a simple hole, then you are basically just drilling out and there's nothing else involved there. But if you're screwing stuff in, and you don't necessarily want those screws up at the top, if you need them to go further down, say you're trying to connect two pieces of wood together and you don't need those screws sticking out, you can use either what's called a counter bore or you can use a countersink. A counter bore is a circular extra extrusion out on the side, and it's circular and it doesn't have any angle other than a 90-degree angle down at the bottom. So if you look at a side profile of a counter bore, it goes down at a right angle like this. These aren't as common, especially in wood. Normally in wood, you're going to see the countersink instead, and that's because most screws have this angle associated to it. So a countersink is going to be this extra piece of extrusion. It kind of looks like a chamfer whenever you're modeling it. So there's going to be this extra chamfer around on the side, and it is at an angle. And what that's meant to do is if you've got a screw, it's meant to actually like take the head of the screw and put it inside of the material so you don't have it sticking out. That's really what we use counterbores and countersinks for. The same features apply to blind holes as well. So, there's not really any difference there other than you can't see all the way through it. So there's a couple of different notes that we need whenever we're talking about holes. So obviously, if you're drawing a hole and you draw it from the top view, it just looks like a circle. So you're going to need some notes in order to be able to determine what kind of hole it is. So what we normally do is we have some symbols that go along with it. If you're describing a diameter, we're going to use the symbol that is a 0 with a dash through it, or the capital letter O. So you're just going to make an O with a dash through it, and that symbol means diameter. The number that you're going to put for the depth, we don't actually write out depth because we're really lazy. What we do instead is we just write an angle, like we write a T with a arrow at the bottom of it, and that indicates the depth of the hole that you're trying to make. If you need to have a countersink, then you're going to put the countersink as an arrow just by itself. Don't actually attach it to any of the other symbols. And the counterbore, if you need a counterbore on it, you're going to use this symbol instead. Okay, so there are a couple of different ways that we can, write these notes out. Let me give you a couple examples. So, for example, if we've got a hole that looks like this, and obviously I'm looking on the side here, there's a counter bore. So I'm going to look at these notes on the left side or on the right side. So it says this symbol is diameter, so it's going to be a diameter of 0.375 inches, and this tells me the hole depth. The hole depth is going to be 2 inches deep. The counter bore is going to be the symbol for how far we're going to be making this extrusion on top. And this counter bore is going to be 0.75 inches in diameter. Notice it's larger, so it's going to be larger than the actual hole size. And it has a depth of half of an inch. Okay, obviously this hole is not to scale because if this was 2 inches and this was half an inch, this should be like 25%, and it's not quite there. But you know what? That's okay. Let's see here. The reason why there's this bottom area is because normally whenever you're making a hole, you're going to be drilling a hole. So the extra part down here is not counted in the hole depth. Because every time you have a drill, if you look at one, it's got this tapered end on the edge. This part, if you were to put a screw in here, this would not actually screw in down in this bottom area. So when we're looking for the hole depth, we're really only looking for however far we go down on the drill to the end before it tapers. That's what we're looking for the whole depth. And if you were actually drilling, say in carpentry or something like that, you would need to use the depth of the drill without using the tapered end, or else you're going to try to screw it in and it's not going to screw all the way in. You'd have to drill down a little bit more. Okay, so there are a couple. Oh, here's another one. Another example. So this one has a diagonal down this way. So this is a countersink. So whenever you're making a note on this one tells me that I'm making a hole that's a 1/4 inch, and it's got a depth of 2.25 inches. And then I'm going to look at the countersink, and the countersink tells me that it is going to be a countersink with a diameter of 1 inch all the way from here to here, from the left side to the right side. That's the diameter, and it's going to have a chamfer angle of 82 degrees. Okay, the angle of cut is going to determine how steep this is. Okay, so if you use a smaller angle, this is going to be less steep. And you're going to use whatever angle that the screw that you're going to use for the object is. So to measure that, you'll measure the angle of the screws. And if you need some more information on how to do that, there's a couple of examples, or there's a description up here just above it. Okay, I'm not necessarily going to make you guys measure the angles of the screws that we have. I don't think that's going to be like super productive. I think if I can get you a good idea on like the holes, I think we'll be pretty good on that one. Okay, so here's a couple more examples, and you can see the different types of holes that we have. So if it goes all the way through, then instead of actually having a depth to it, we're just going to say through, Thru, through. Okay, that means it is a through hole. Yes, that is not how you spell through in English. Through in English is Through, but that's okay. In machining language, we just say through, Thru. So rejoice in not having to use the English teacher version. So I look at this one, I can see through it. So this is a through hole, and it's a simple hole with a diameter of zero point 0.5 inches. The one on the right side looks like I cannot see through it, so it's going to have a drill depth. And to look at it from the top isn't super helpful, so if I look at it from the side profile, that normally ends up helping a great deal. This one tells me that it's got a diameter of 0.375, so it's going to be on the bottom part, and it's got a depth of 2 inches. Remember, that's going to go from here all the way down to the bottom. The counterbore is 0.75 across, and it's got a drill depth of 0.5 inches. Okay, the next one is I'm looking at these notes here from the top, and it says that it's got a diameter of 0.25. It's got a I'm sorry, it's not through, it's got a depth of 2.25 inches. It's also got a countersink on it, and that countersink has a diameter of 1 inch, and it's got a cut angle of 82 degrees. So I'm looking here, and these notes on the top should, in your mind, give you an idea of the kind of hole that's being created here. The next one, I'm looking at it, I can see through it, so that's zero point 0.5 inches through. And there's a counterbore as well, and it's got a diameter of 0.75 and a cut depth of 0.625 inches. So these are a couple of different eyes. Oh, and by the way, so like this is like a cutaway view, because like if we looked at this block and we looked at a side view of it, these would all be hidden lines. So they made a section view out of this by saying, hey, we're going to make a side view of it, but we're going to like make our side view of the object that's been cut in half. And you can always tell whenever something's been made a section view because it's got these diagonal lines through it. This means that the object has basically been cut and you're looking at it through a cut section of it. Okay. Here's a couple of practice problems that you're going to do. So what I would like you guys to do is I would like you to make notes of whole notes of A, B, C, and D. Oh, I'm sorry, there's no D. Sorry. I want you to make whole notes of A, B, and C. And then after you make the whole notes of A, B, and C, we're going to start our task, and this will probably take 2 days in order to be able to do. So in physical class, I'm going to make an assignment for these whole notes and the whole notes that we do in class. If you're virtual, you've just got to worry about A, B, and C. Okay, so try to make the whole notes for A, B, and C. And then on the next day, I'm going to make an assignment that is going to be creating a 3D model from scratch. So I'm going to be giving you guys the drawing design of these trammel toys, which is ultimately what we're going to end up building later on. So we're going to have these toy kits and we're going to be assembling them together and seeing if they actually work correctly. And we're going to be making a 3D model of this, and I'm going to give you the dimensions of the drawing, I'm pretty sure. Let's go ahead and read through the instructions on that, and when I make the next video, I'll review these. Okay, so what we're going to do for task one is um, now you're ready to measure and properly document the dimensions of a trammel toy part, including the hole sizes. Uh, Part 1. In the same trammel toy team you formed in the last activity, retrieve your trammel toy parts kit from your teacher. If you're digital, then you're going to be doing this on your own. You're all solo. You're going to divide into two pairs. Again, if you're digital, you're doing the solo. And we're going to complete both of the following tasks with our partner. If you're digital, you're not actually going to have a physical version of this trammel toy. What you're going to have instead is I'm going to give you a 3D model, and you're going to have to measure it using the 3D model. So I'll show you guys how to do that later on the next video. So for now, this is just going to be making holes part 1. So this is 1.3.1, making holes part 1.